All right, today we're cracking open the digital brain that powers, well, pretty much everything in our modern world. We're going to demystify what is arguably the most complex object humans have ever created, the microprocessor.
So let me start with a big question for you. What do you think is the single most complex thing humanity has ever managed to build? Are we talking about a space station? Maybe a particle accelerator? A modern jetliner?
Well, the answer might actually surprise you, because chances are you're holding it in your hand right now. It's the microprocessor. This tiny little slice of silicon is basically a miniature city, home to billions of microscopic switches, all firing in perfect harmony to power our world.
It's just an incredible piece of engineering when you stop and think about it. But how in the world did we manage to shrink a brain that used to fill a room down to something smaller than your fingernail? And, maybe more importantly, how does this little city of switches actually think? How does it do math and make decisions? That's exactly what we're going to dig into.
You know, to really understand how we got to micro, we first have to look at the macro. So let's jump on our time machine and see how this incredible journey of miniaturization all got started.
So, meet the ENIAC. This was one of the very first general-purpose electronic computers, built back in 1946. And this thing, it was an absolute monster. We're talking 30 tons, filling a 15,000-square-foot room. It ran on 18,000 super-fragile, power-guzzling vacuum tubes, and after all that, it could do about 5,000 additions per second. I mean, the phone in your pocket is literally millions of times more powerful. It's just staggering.
So how did we get from that behemoth to the chip in your pocket? Well, it happened incredibly fast, thanks to a few game-changing inventions. It all kicked off in 1947 with the transistor, a tiny, reliable switch that replaced those big, clunky vacuum tubes. By 1965, we could cram about 100 of them onto a single chip. And then, in 1971, came the big one. Intel created the 4004, the world's very first microprocessor, putting an entire computer brain onto one piece of silicon.
And this whole crazy pace, it was basically running on rocket fuel, an idea that came from Intel's co-founder, Gordon Moore. Back in 1965, he made this incredible prediction that the number of transistors we could fit on a chip would double about every year. This became known as Moore's Law, and it turned into a kind of self-fulfilling prophecy that has pushed the tech industry forward for decades.
Okay, so Moore's Law explains the how we managed to pack so much power into such a tiny space. But what about the what? What's actually inside that little computer brain? What are the key parts that make the whole thing tick? Let's zoom in and take a look. So at the highest, most basic level, any computer really boils down to three main parts. You've got the central processing unit, the CPU, that's the brain doing all the heavy lifting. Then you have the main memory, which is kind of like its short-term workspace. And finally, you've got input-output, or I/O, which is just how it talks to the outside world. You know, your keyboard, your mouse, your screen. Now, if we zoom in even closer on the CPU itself, you'll find that the brain has its own internal organs, so to speak. There's a control unit, which is like a traffic cop directing all the information. There's the arithmetic and logic unit, or ALU. And then there are these little high-speed storage spots called registers. Okay, the ALU. This is where the magic really happens. You can think of it as the computer's super-fast calculator. Every single calculation, every logical comparison, is this number bigger than that one? It all happens right here, inside the ALU.
So if the ALU is the math whiz, where does it get its numbers from? Well, that's where registers come in. Think of them as the CPU's personal, high-speed scratch pad. They hold the exact pieces of data the ALU needs at that very second. And because they're built right into the processor, grabbing data from them is way faster than going all the way out to main memory.
All right, enough theory. Let's make this all a bit more real. To see how these parts all dance together, we're going to look at one of the most important microprocessors ever made, the legendary Intel 8086.
This chip, released way back in 1978, was an absolute powerhouse for its time. It was a 16-bit processor with 29,000 transistors. But its real claim to fame? Well, its slightly different sibling, the 8088, was chosen by IBM to be the brain of the very first PC. That decision basically set the standard for the x86 architecture that still powers our computers today. So what made the 8086 so special? Well, part of it was this really clever design. It essentially split the CPU's job into two specialized teams. You had the bus interface unit, the BIU, which was the fetcher. Its only job was to go out and grab the next set of instructions from memory.
At the same time, the execution unit, or EU, the doer, was busy executing the instructions the BIU had already fetched. This assembly line approach is called pipelining, and it made the CPU way more efficient.
But the designers of the 8086 ran into a really big problem. A puzzle, really, that had to do with memory. And solving it required a true stroke of genius.
Okay, so here's the puzzle. The 8086 is a 16-bit processor. That means its registers, its little internal scratch pads, can only hold a 16-bit number. But it was designed to talk to a whole megabyte of memory. And to address 1 megabyte, you need a 20-bit address. You see the problem? How do you fit a 20-bit key into a 16-bit lock?
The solution was, honestly, brilliant. It's called segmented memory. Instead of trying to use one big 20-bit number that wouldn't fit, they used two smaller 16-bit numbers. They used one number, the segment, to point to a big block of memory. Think of this as the street name. Then they used the second number, the offset, to point to the exact spot within that block. That's like the house number.
Yeah, I know, the slide has some hexadecimal numbers on it, which can look a little intense. But you don't need to worry about the math. Just remember that street name and house number idea. By cleverly combining a segment and an offset, this 16-bit processor could generate the full 20-bit address it needed to talk to a much bigger world of memory. It was just a really elegant solution.
So that's a cool little history lesson, but why are we talking about a chip from over 40 years ago? Why does it still matter so much? Well, because its legacy is, quite literally, everywhere.
And here's the really wild part. The fundamental ideas pioneered in the 8086, things like that pipelining trick and that clever memory management, they are still the foundational DNA of the processors we use right now today. Every modern PC processor has to be backward compatible with the basic language of the 8086. Its design philosophy has echoed through the decades.
And just look at how far we've come since then. The 8086 had 29,000 transistors and ran at 5 megahertz. Now, fast forward just over 20 years to the Pentium 4, we're not talking thousands anymore. We're talking 42 million transistors running at 1.5 gigahertz. That is Moore's Law in action, and it is a truly mind-boggling explosion in power and complexity.
So the architecture of the 8086 and all of its descendants, it basically defined the entire PC era. But as we start to push the absolute physical limits of silicon, it raises a huge question. The building blocks from that time got us this far, but what will the next great architectural leap look like? What will be the next 8086 moment that redefines computing for the decades to come? Now that is something to think about.